this video, I'm presenting an algorithm to solve first-order differential equations using numerical methods, RK2 of first order and second order. But first, I am showing a flowchart, so this algorithm can be implemented in any programming language. So first, of course, we're going to receive the parameters or inputs, the differential equation f, the initial conditions, the number of iterations, the step size, and the exact solution that is optional. Just to compare, we'll see this in the code more detailed. Well, then first we ask if h was provided. That's because I based my code on a previous Euler's method I had, and if it was, we're going to keep the given step value. If not, we're going to set a default value of 0.1. Then we're going to initialize our vectors, arrays, list, depending on the program, x, and the g values for the second order and the fourth order RK2 method. And well, I think this word already says it, but initialize. With initialize, I mean set them equal to 0. Except for the initial values that are already given. And this depends on the programming language you're using. Basically, if it's not R or MATLAB, you're going to set the first value of your array or your vector to the initial value. If this is MATLAB, this is going to look like this. We're just basically setting the first element to our initial values. Then we're starting a loop that goes from 1 to the number of iterations asked for the user. And well, first we're computing the next x. That this is basically the next value is going to be equal to the value we already have plus h, plus our step size. Then we're computing the slopes for the second order method. And well, this just follows this. I didn't include the math because I didn't want this to look like formula sheet, but you can look it up. And this is just going to be the first k is this, and the second one is just the same, but adding the value we're in plus h, and for the g value it's exactly the same. And then we're computing the next g value for the second order, and this is just that the next value equals to the this is an equal to the previous value plus the step size times the slopes over 2. And then we do the exact same, but for the fourth order method, we calculate the slopes. Then these are a lot more larger, so I'm gonna skip the writing. We'll see it later in the code. And once again, we're computing the next g value for the fourth order method. Then we're asking, is k less than the number of iterations? So let's say, oh my god, I just realized it's a little bit confusing for this to be k. Well, imagine this is just an a or any other letter, but this is just a counter for us to keep adding iterations. This has nothing to do with this case. That's an improvement we could make. But well, We're asking that if the user asked for just one iteration irrationally, we're asking is 1 less than 1? No, then we continue. But if it is, then we're going to add 1 to our counter and repeat the whole process. That's a loop basically. We're starting from the value 1, then asking if we have completed the number of iterations, and if not, we add 1 to our counter and repeat the whole process, but for the next value. And we're adding that to our array or vector or list. Well, and if we finally reach our number of iterations, then we continue and plot our J and or J and X for the second order and fourth order methods. Then if the exact solution G is provided, because once again it's optional, then we're also plotting it to compare our results. And if not, well, we just skip that and we print our vectors, arrays, whatever, and our final approximations. So we're going to get something printed like our initial condition say 1, blah 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 blah, and or J for the Runge-Kutta second order method, blah 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 blah, and the same for the one. Here's the side-by-side algorithm and actual implementation in MATLAB. We'll first explain the code before making an example and matching what's going on here with what's going on here. Okay, so first I created my function called RK methods, Runge-Kutta methods, and it's receiving these parameters, the same as here. Then this part of the code, so it's asking if H was provided. Here it's empty. And if it was empty, we're setting H as our default value. And if not, well, we're just going to continue. Then we're initializing our vectors from up to 1 to n plus 1 and filling them with zeros. And the same for 2 j's that we're going to have. And this is what we're saying. Then next, well, the first value that we're having is the initial conditions given. And it's going to be the same for this one. And then we're starting our loop. First, we're calculating our x values. And it's just going to be like, if our step size is 0.1, it's going to be 0, 0.1, 0.2, 0.3, and so on. That's the easy part. Then we're calculating the Runge-Kutta second order method. And well, this is just calculating the slopes. And then our final values. We're using the formulas that I explained it before, but just with the MATLAB syntax. And then we're doing the same for the fourth order method. We're calculating the fourth slopes or tangent lines. And here we have the formulas, and then using that to store our next value or next G value. And finally, we're plotting the results. Here we create a figure. And here we're plotting X or Y, setting a color and the design, the width of the line, and well, this is for the legend that's going to appear on the side of the figure to specify that that solution is the second order Runge-Kutta solution. And the same for the fourth order. Then here we're asking if
or G solution was provided. And if it was, we plot it, we create the vector and then plot our vector. Then this is just formatting, clarifying what we're doing. We're comparing the both methods, setting the labels, the legends, and here we are plotting our results, like for the final value we got for x, the final value we got for both j's in the second order and fourth order solution. This is going to be a lot more clear once we do an example.
So before visualizing the numerical solution by the Runge-Kutta plotting, I want to solve the differential equation we're gonna use analytically to compare, and also because we're gonna input that function as our G solution. So I'll take first order differential equation, let's say a simple one. Okay, we can rearrange terms and integrate to find our solution. First we rearrange our terms. I just moved this here, and well, mathematically it's not move, but for practical reasons we're gonna say move. And then integrate both sides. This is just the natural logarithm of y, and this is gonna be x squared plus c. Then we use exponentials to get rid of the natural logarithm over here, and well, this is just j, and here we have this, and by the power property, this is just that, and this is just another constant, so we write it as so. And then let's give an initial condition, say this. So we're evaluating our function in x equals 0, which is going to be 1. Well, the whole thing is going to be 1. So y equals 1. So c equals 1. So we substitute this in here, and we just get that our solution is this one. Alright, this is just a really simple differential equation, but we'll compare it to our program.
So I already typed our anonymous functions that we obtained. Well, the differential equation we decided to implement, and the exact solution that we computed analytically in our code. This is optional, but just to have a clear comparison. And oops, I'm sorry, I had the numbers. We're gonna call our function. I'm sorry, I'm a really slow typer. Okay, so first we're gonna put our differential equation, then our initial condition. We said j was going to be equal to 1 when x is equal to 0. That's our initial condition. Then as for number of iterations, let's give a neat number, let's say 10. Then as for step size, something that's not 0.1, so we can demonstrate that our code works. So 0.25 and or exact solution. And we're gonna see what this plots. Okay, so here we have our graph that already shows the exact solution, that's the black line, or Runge fourth order approximation in clear blue, and on a lighter blue or cyan is our second order one. And here we can see our vectors. Like I said, x just goes adding up 0.5 each time, and or Runge that's so difficult to pronounce. Solutions and or fourth order one. That is what we have right here. And we can see that the fourth order approximation is a lot more closer. And actually, we could compare it to Euler's methods that I have a code from the previous semester to see how different this is. And we're gonna give the same parameters. It was F1, 0, 10 steps, 0.5 as our step size, G, and that's it. Okay, see how different our approximations were? This is the actual solution, and this is our numerical approximations. And now I want to talk about improvements that could have been made. First of all, checking our parameters, because we only checked if h was given or not, but users can make a lot of mistakes like me and try to input a negative value or give a crazy number of iterations that will slow down the algorithm a lot, or give a really small, or well, not a really big step size, so the accuracy of our solution wouldn't be as good. And also, I think it will be great to give a error margin, like plot the difference between the actual G value and the G value given by or Runge-Gupta method. See, or residuals, the difference between this J value 349 and the value given by our method. And what else? I'm changing this K because I noticed that it's really confusing because we're also using K for our vectors and our slopes. Change it for an I. It's I based my code on this previous Euler method I had. And I also used K. But I think that's it. We could also talk about other functions, like I'm gonna speed up this part because I'm a really slow typer. Okay, I wanted to include this other example because here the actual solution is 1 minus x. So if we choose a step size of 0.1 and well, actually we could have just omitted this, skip this, because as I said, our default value is 0.1. But what I wanna emphasize then is that as we approximate to our maximum value for j, so as x is more close to 1, we're gonna reach division by 0, and that's gonna be an error. So our maximum iterations could be 9 because our x goes from 0 to 0.9. So a future improvement will also include warnings for the user, so they don't get random error or other errors, because we're not checking that under code. We're not considering all the possible errors or all the possible things that the user might not be taking into account. But this is our Runge method, and I chose cases that weren't as accurate, so we could see more the difference between the actual solution and our other methods. But we can see that they're a lot better than the older because they take more tangent lines. And I think we can have any other improvement other than checking for errors, showing the difference between our values, and changing this K that's been bothering me. But that's it. Thank you.